Yeah, Umang, let me know. So I think we can start. So whenever you are ready, and we can start.
Just give me a few seconds. Yeah, please go ahead.
Okay. Okay, so let me introduce the speakers. So we are delighted to have Ramanathan Thinniyam as the speaker today. Ramanathan is currently a postdoc at the Max Planck Institute for Software Systems. And he obtained his BTech from IIT Madras, his MSc from Chennai Mathematical Institute, and his PhD from Institute of Mathematical Sciences in Chennai. So he has been working on theoretical aspects of verification of multi-threaded programs in particular, and he has published in conferences such as ICAL, POPL, TACUS, and his works also received an EAPLS Best Paper Award as well as a POPL Distinguished Paper Award. So Ramanathan, thank you very much for accepting our invitation and agreeing to speak at the STCS seminar. So over to you, Ramanathan. Thanks.
Thank you, Shivashish. Thank you for the introduction. I'm very happy to be here and to share our some part of our work. So this is about context-bounded verification of multi-threaded shared memory programs. So this is work that I have been doing with Pascal Baumann, Rupak Majumdar, and Georg Zetscher. And we are all at the Max Planck Institute for Software Systems at Kaiserslautern. And so let's dive into this. So what are these multi-threaded shared memory programs? Let me start by sharing some example code. So here is a program where there is a shared Boolean variable x, which is set to 0. And there are some initial couple of programs, A and out, which are put into the task buffer. And the body of A is some C code in some C code like syntax looks like this. So it says that if the global variable x is equal to 0, then spawn a new copy of A and also a copy of program B. And then after that, there is a statement which says if star. So the star is some kind of non-determinism. And if star, then call itself recursively, right? So there is some dynamic spawning, and then there is this recursive call. And after the call returns, it again checks if x is 0, and then it could spawn a couple more things, right? So, and then so B is some other program which has some body, and out is some other program which is right now which is not important to us. So overall, the setting is that of you have a program where you have finite, you have some variables which take say Boolean or finite values. You can have spawning of new tasks at any time. That is non-determinism. And as we shall see in a bit, there is also some kind of non-deterministic scheduling of different tasks that will be going on. So, so these kind of programs are found in many places, like operating systems.
Question: Is that
question?
Okay? Is it okay to ask in the middle?
Sure. In fact, I will go through like a sample run of this program. Maybe I can go through that and then take out a couple of minutes, or if you want to ask right now, that is also okay.
Yeah. Okay. So the star means if you wish, you execute that block, or you don't.
No, so it is some non-determined. So there are places where when you're designing something, then you would, it is a non-deterministic choice. So it could be that it gets executed. It could be that it does not get executed.
Yeah.
And during the analysis, you would want to account for all possible runs in a sense. So where this non-determinism is coming from, it could be from multiple places, right? It could be because initially you are just designing something and then you want to fill in some gap later on. You want to choose one of two different modules that you want to run at this point. You know, for various reasons, there could be some non-determinism, various things that you model as non-determinism in a program.
Got it. And this semicolon means still sequential execution of those two or parallel? The spawn A, spawn B.
Right.
there is a semicolon between, that means these are both spawned in parallel, or they
Yeah, so they will both be spawned. Yes.
One after the other.
One
Okay.
after the other. Yes, they will be spawned one after the other.
Okay.
Yeah.
No.
So
So,
they will be.
yeah. What does that mean? That means they will be running in parallel with each other, or after
Essentially.
A finishes. Okay.
Essentially. So we will soon see. I will just go through a small run of the program, and then you might see like what is going on.
Thank you.
Yeah. So these are there in different
sorry.
kinds of yeah.
Yeah, there is a small question. Maybe it will be answered when you go through the code. So there is a question which says, "What is spawn?" So,
right. So yeah, maybe I will just go through this. Right. So here is this example. So there is some initial program configuration. So namely that there is some you have this the state of all the global Boolean variables. So here there is only one variable x which is set to 0. And then initially there is no thread which is being executed, but there are these couple of threads A and out which have been spawned. So that is the meaning, right? So there are a couple of threads which have to be run. Couple of tasks in a sense, couple of tasks which need to be executed, right? So so there is some kind of non-deterministic scheduling. And so here, for instance, let us say that we pick up A. The scheduler chooses A to be run, and then this starts executing, right? So and then so it is the first line of this A is being executed. So it checks that indeed x is equal to 0. So it will spawn a copy of A and a copy of B, which is added to the pending threads, as you can see. And then it goes to the next line. And then here, suppose the non-deterministic choice that is made is that actually there is a call which is made, right? So there is a recursive call which is made to itself. So here we note that now you see that in the currently executing thread, I've written A3 and A1 with 2 boxes. So you can think of this as a stack, right? So a call has been made. And the A3 indicates that when the call returns, then it will get picked up again starting from A3, right? But the call which has been made now, it starts running at A1, right? And now suppose again, this thread is stopped by the scheduler. And again, non-deterministically, it can choose to bring in something else. So let's say it brings in A and it starts running this A, right? So this is basically how you should think of this, right? So you have these tasks which are spawned and they can start running. And then when they make recursive calls, then they can start building up a call stack. And all of this switching in and switching out of tasks is just thought of as non-deterministically, right? So in general, you can have an arbitrary configuration of this program where you have some currently executing thread which is A in at line A1, but there are a lot of different kinds of threads, right? So some of them are let us say uninitialized threads like the green A and the pink B, but there are also a couple of threads which have made a number of recursive calls. So the first one has a stack of 3 and the second one has a stack of 4. And in general, the point is that there are these arbitrarily many threads, and each of them can have an arbitrarily large stack.
So Ramanathan, just a question, maybe if you could explain this a little more, that when you say A3, A3, A1 in that red box, what exactly it means?
So it means that there was a which started running, and then it made this recursive call at line A2. So when the recursive call will return, then it will pick off at A3. It will start executing A3 when the return happens. So that is, so I put an A3 there, and then again it has the recursive call itself here has made one more call, right? And then it is at A1.
Okay.
Right, and then at this point, when this third recursive call was made, the scheduler decided to pull this thread out, stop executing it, and it switched in something else.
Okay.
So which is why it has, there is this partially executed thread which is hanging around in the pending threads.
Okay. Okay.
Yeah. So so more abstractly, you can just think of it as there is some global state, which has one of finitely many values. So these are all the different, there is some valuation for the different global variables. So you can think of that as, G1 corresponds to some x is equal to 0 and y equal to 1, something like this. There is at most one active thread at any point of time. And here now we can sort of move away from the program code and just think of this as a stack where it has the stack alphabet is some finite alphabet, right? So from the program standpoint, you can think of it as the places where you would have sort of returns to the program where you would have to continue. So those would be the line numbers which would correspond to these letters such as like A and B, right? But in the abstract, you just think of it as a stack which has some finite alphabet, right? And there is a buffer which just has some number of stacks of inactive threads.
So the instruction counter for each thread is not part of this thread buffer state. So where each call is.
Well, it is there. So that is why I'm saying that. So you can think of the entire program as having only some finitely many lines, right, of code. So what you have in so the stack alphabet will essentially contain what you need to write down over there will be things like what is the line number that you will return to. So that is essentially what it contains. So in a sense, the source of unboundedness in the way we are modeling this.
Sorry to interrupt. So I was want to ask. So are you only considering the global variables, or also you are thinking of the local variables that each thread has? So in this case,
so we are not here. We are not. I mean, the way this abstraction is made, we have not made place for the local variables. But in essence, you can think of it as there would be a way to store the local variables onto the stack and then use the global state to pass it back and forth. So in that sense, you would still be able to model this in this manner, the way we have shown it here. But it is just to make things simpler for us in the analysis later on, in a sense.
Okay.
Yeah.
Thanks.
Yeah. So you can have local variables, but we can sort of abstract it away by sort of passing it back and forth between the stack and the global state. So in this abstract sort of picture, so you can see that suppose you have some global state. This global state can be changed by the active thread, right? So essentially, this is why this is this shared memory, right? So essentially, whenever a thread is made active, it can change the global variables, and in this way, it communicates in a sense with the other threads, right? So here it changes the global state from G3 to G4. So at the same time, the active thread can also push a symbol onto the stack, and essentially, a recursive call is modeled by this push. And similarly, the return of the recursive call is a pop operation. So in addition to this, we have the spawning of tasks. So again, while doing this call, it could also be, you can also think of it as spawning some tasks, right? So in the abstract, you can think of the operation of these programs in this sense, right? So you have some global state which can be accessed and changed by the active thread. And the active thread can do pushes and pops, and it can also spawn some new things which get added to the buffer. So maybe this is a good place to pause for a minute or two, because then essentially we will move on and talk mostly about with respect to this abstraction rather than in terms of talking in terms of code.
So here on the left side, you have the A and the B. So this essentially, it shows a stack, right? So you have that in the stack, you have A at the bottom, and then you have B, and B is currently the active thread.
No, so maybe I did a sort of a bad thing by reusing the A and the B from the example. So here you should think of, the A and B are just sort of abstract alphabets, right? So A so could be like A1 or A2, and B could be some A1, A2, B1. The various. It could be various things, right? So here, just think of in this abstract setting. Just think of these as there is some finite alphabet. Here we just have some alphabet A, B. That's it, right? So in this sense, we are moving away from the program where you have line numbers and various data which gets pushed onto the stack, to like this more abstract model where you just have a stack which contains some finite alphabet. Here the finite alphabet is AB.
Yeah. I was just trying to understand, like, what does the alphabet here correspond to? Is it the specific instructions of the thread, or?
Yes, it would be, right? So like I said, when you make a call, then at some point when you return, you would go back to the previous execution to some place where there is a return, right? So essentially you can think of it as the line number over there. So, but the important thing here is just that all of these things are some finitely many things. And so you have some finite stack alphabet.
Okay.
Yeah. So even if you wanted to push something slightly more complicated, you could, sort of change it into, say, a binary string and then push it, for instance, right? So you could still get like you would still have a finite stack alphabet. Right. So if you wanted to push some kind of number onto the thread, for instance, then maybe I'm moving away from, yeah. All right. So now this is about verification of such programs. So
sorry, can I go back to the code actually, even though you?
Okay.
So now, suppose I just called A, or I want to see what happens when an execution of A starts. So at that time, there is only A in that diagram, and in that many stacks that you drew, there is only one A at that point. Or?
Yeah. So if you see the initially there is an A and an out which gets spawned, right? So both of them are there in the pending threads.
Okay. And then
the scheduler will pick up one of these threads non-deterministically to execute. So here we say that, okay, the scheduler non-deterministically chose A to pick it up and start executing.
Yes. So at that time, then how many, like those stacks that you had, those towers, how many will we have? There will be one for A, another for A, and another for B, because A and B both have been spawned. How do I think?
Yeah. So the next step, when they are spawned, then you see that the spawned A and B have been added to the pending threads. So there you have these stacks over here. Yeah.
Of height 1, right?
Yes. Essentially, these are of height 1. Yeah.
Okay. And then a new A may or may not be added based on non-determinism.
So this is this A2 is a recursive call. It's not a spawn. So here is where you see that the stack height of the executing A gets increased because it has made this recursive call.
Okay. So when we do A2, height of one of the stacks increases or doesn't increase because it is non-deterministic, right?
Exactly. Okay. Yeah.
And then when we finally get to A3, let us say that it was not, the non-determinism didn't happen. So another A was not added. Then we get to A3 and completely, and suppose X was 0, then two more things are added to the.
Exactly. Okay. Yeah. So if X is 0, then another copy of B and A will be added to the pending threads. Yes.
Okay. So at that point, there are something like, apart from out, there are 5 of them or something.
Essentially there would be one executing thread and 2 copies of A, 2 copies of B in the pending threads, as well as the out.
Okay, got it.
Yeah.
Thank you.
You're welcome. Yeah, so we want to verify such programs. So in particular, for instance, one property that we might want to check is that of safety. So does the program reach an error state? So now this can be seen as the reachability of a target global state, right? So because if some program reaches some error state, then essentially you can think of it as, we just want the computation to stop, right? So, and the program would want to communicate, the running thread would want to communicate this to everybody else that, hey, this error state has been reached. So, and the way to do this is via the global state. So essentially we think of this problem as there is some target global state, one out of the finitely many global states, and can we reach this? And similarly, another question that you can ask is, given some program, does it always terminate? And here we mean terminate for all possible non-deterministic choices made. So already you see that there is this combinatorial explosion because of the non-determinism, and which is why when you have such programs, then it's usually difficult to reproduce errors, and it's difficult to debug them. And so another thing that one could be interested in is the notion of fairness. So we say that a fair run is one in which every task which can be scheduled is eventually scheduled by the scheduler. So now we can ask, does every fair run of the program always terminate? So there could be some way of scheduling things in a silly manner where you just ignore certain threads, for instance, which could be the reason for non-termination. But we want to know if under this condition of the scheduler that it is fair, is it the case that the program always terminates? So these are some of the different kinds of problems that one is interested in verifying, certain properties that one is interested in verifying. And naturally, the question is, what is decidable? And unfortunately, there are well-known classical undecidability results because, as we know, if you have two stacks already with a global state and two stacks, you can simulate a tape, so essentially a Turing machine. And we know that any non-trivial property of such systems will be undecidable. So there is a need to place restrictions in order to get decidability. So in our setting, the restriction that we talk about, that we focus on is that of context boundedness. So here we define the notion of context switch number. So here we see that under each of the threads, there is this number that has been written, right? So the active thread has a 0, and then there are all these other numbers which are written. So these are meant to indicate the number of times a particular thread has been switched out. It was active and then it was switched out and put back in the task buffer, right? So what do I mean by that? So for instance, here, this active thread was a 0, and when it got switched out, the number increased to 1. Right? So now at this point, there is no active thread. Something has to be switched in by the scheduler. So let's say this stack is switched in. So here we do not increase this count from 2 to 3. Right? So you increase the count whenever you pull the thread out of the active thread. So here we say that a k context bounded run is one in which every thread is swapped out in at most k times. So this means that the biggest number that can occur out of on all the threads is at most k, right? So why does this lead to decidability? This is because if you look at the two stacks which simulate a tape, this is essentially what I would call this the slinky trick, right? So you cut the tape where the head is, and then it sort of forms two stacks, and then you go back and forth between the two stacks. So now, since you have to go back and forth between the two stacks to simulate the tape, and now if you fix this number k, saying you can only move away from a stack some fixed number of times, then this means that we cannot simulate the Turing machine anymore. So this allows us to get decidability for a number of different problems. So this context-bounded analysis was started in the 2000s already by Kadir and Rehoff, and many other researchers have also worked on this. And note that it is an under approximation of the system behavior, right? So we are sort of taking some multi-threaded program and saying we will only look at those runs where for some fixed number k, the number of times any thread is swapped out is k, right? So this comprises of some subset of the all possible system behavior. So it's an under approximation. But it is useful in practice because many bugs can already be detected with a low number of context switches. And in this context, now the safety problem becomes, we are given some program P and some global state G and some number K. And is there a K context bounded run of P which reaches this global state G? So other problems can also be rephrased in this setting. And previously, Atik, Bojani, and Kadir showed that if K is given in unary, then the safety problem is in 2x space. And naturally, one would like to see if it is possible to get a matching lower bound. And what about the other properties? What is the complexity of other properties? And so these are the kind of things that we have been working on. And so in our ICAL 2020 paper, after a gap of about 10 years, we finally resolved this issue of the matching lower bound and showed that, in fact, the safety problem is 2x space hard. But here, in fact, it is 2x space hard already for a fixed k for just one context switch. And this was really surprising to us, because we had been thinking that maybe if you fix the k, then it's x space, and if k is part of the input, then maybe it's 2x space. But it turned out that already for k equal to 1, it's 2x space hard. We also showed that the FAT termination problem is Ackermann complete. And more recently, we have shown that safety is X space complete if you bound the number of threads. So here, when I say bound the number of threads, I mean the number of sort of partially executed threads. So if there is something which has not yet been initialized, then that is not counted. But if something has been executed and then it has been pulled out in between, if you bound the number of such things, then safety is X space complete. We also have results for a simpler model, which is called asynchronous programs. So you can think of this as a model where you have this sort of dynamic spawning of new tasks, but you don't have any context switching. Every thread just runs to completion. So these are the different results that we have obtained. And in this talk, I will just try to give an overview of the sort of key ideas of this result, that safety problem is 2x space hard. So here is also, this is again a good place to sort of pause if there are any doubts.
So in this recent result, this popular 2022 result that you were talking about, so it's bounded number. When you say bounded number of threads, you means that you mean that the number of threads which have executed that you have a bound on. Is it?
No. So you can think of it as so suppose you have some, say, like so you can think of it as there are a number of tasks which are uninitialized and which are sitting in some buffer, and then there are, say, only 4 places or 4 threads where you can be running things, right? And at any one time, let us assume that only one of them is running. But if you want to run a new task, suppose there are 4 threads and you want to run a new task, and if all the 4 places already have some partially executed things, then you cannot start a new task. So one of those 4 has to finish executing, and that space has to be emptied out before you can pick up another uninitialized task from the buffer and start running it in that spot. So that is what I mean by bounded number of threads.
Okay.
Yeah.
And when you say, like, there was something about global state, reaching a particular global state. So what do we mean by a global state? Global state of one of the executions?
Yes. So essentially, is there some execution? So the global state in the abstract setting is just one of finitely many values. But in the programmatic setting, you can just think of it as the values of the different global variables. So the safety problem is the question of, is there some execution which will result in this certain set of global variable values, or in the abstract setting, a particular global state. Does that make sense?
Yeah. So questions like, is there an execution where there are 700 stacks with A at the bottom? That is not considered a global. That's not.
No. So we are not thinking about. So though in a sense, so those are the sort of the local configurations, right? So of the threads.
So scheduler sort of is not.
Sorry.
So scheduler state is not part of the configuration.
So we are not looking at, so we have just assumed that there is non-deterministic scheduling. We are not going to think about, we're not going to assume anything about what the scheduler is going to do, that it can do anything. And for all possible sort of interleavings or all possible executions, we want to make sure that some error state is not reached. Okay, so shall I move ahead, or are there more questions?
So I have a question. So what do you mean by interleaving? You said there is only one active thread, right? At any time.
So what I mean is, so you can, there is a scheduler which at every time point, it can decide to let the whatever active thread is there, that can continue to run, or that can be pulled out and some other pending thread or a new task can be started, right? It can start to run something else. So
a scheduler for each core you are saying, right? I mean, for each core you have a scheduler kind of thing.
Yeah, so here actually in a sense, I mean, like the way we are looking at it, there is only one active thread or like one core, right? In a sense, the way the abstraction that we have here is of that sort, right? So and yeah, so maybe. Right, so that is at any instant of time there can be at most one active thread, and the scheduler, I mean, basically there is non-deterministically you choose either to continue running this active thread, or it could be that it gets swapped out, put into the task buffer, and like some other thing is brought and made as the active thread, and that thread starts running instead. Does it make sense?
Yeah, I can see. Yeah.
Okay. All right. So, so in the remainder of this talk, we will first start with some 2x space hard problem, and then show that it can be reduced to safety. And so for this, basically, we will first look at introduce Petrinets and show and talk about a particular X space hard problem. Next, we talk about asynchronous transducers. And finally, we show how to get a succinct version of Petrinets using transducers, such that the corresponding problem for the succinct version will be 2x space hard, right? So let's look at Petrinets first. So here's a Petrinet, right? So so what is this? Is a model of computation where you have a number of places. So the places is a set P, which is P1, P2, P3, P4 here. And there is another set which is called the transitions. So T, which is T1, T2, and T3 here. And here we also have these two black circles, which are sort of like two tokens, as we call them, which are put inside place P1, while there are no tokens inside P2, P3, and P4, right? So this is essentially a configuration of the Petrinet, namely the number of tokens that is placed in each of these different places. So that's called a marking. So this marking M has M of P1 equal to 2, whereas M of P2, P3, P4, and are all equal to 0. Right? So now, suppose we fire this transition T1. So then this means that we can pick up one or more tokens. If you pick up one token from P1, then it will get placed on P2 and P3. Right? So then you will place one token each in P2 and P3 like this. So now we have a different configuration, basically a new marking M prime, where you have one token in P1, P2, and P3, and 0 tokens in P4. So again, you can fire this transition T2, and this means it will take away one token each from P2 and P3, and it will add one token in P4. So now we have a new configuration M double prime, which has one token in each of P1 and P4, where P2 and P3 are still empty. And finally, by firing this third transition, you can move this token from P4 back into P1, right? And you get back to the original marking, right? So essentially, this is, I just wanted to show a sample run of a Petrinet in case people hadn't seen this before. And the problem that we consider is that of coverability. So what is this? So we say that a configuration or marking M double prime is larger than a marking M prime if for every place P, the number of tokens of M double prime in place P is more than the number of tokens in the place P for M prime. And so the coverability problem says, given some Petrinet N and some markings M and M prime, is there a run of N starting from M, which reaches some M double prime, which is greater than M prime? And we know by a theorem of Lipton that coverability is X space hard, right? So this is the X space hard problem. And now we talk about asynchronous transducers. So what are these? So you can think of this essentially as an automaton which accepts pairs or in general n tuples of words. So here, can you see my pointer? So that's the start state, right? So Q1 is the start state. And it reads A comma B, right? So it basically, this is a transducer which accepts pairs of words. So for the first word, it reads an A. For the second word, it reads a B. And then from Q2 to Q3, for the first word, it doesn't read anything, this epsilon, and it reads a B here, and here it reads a B and an A, right? So, and then you can define the language of a transducer as the set of all tuples of words it accepts. So in this particular case, for this transducer T, the language of T is just a singleton, right? So it's just one particular tuple, AB, comma, BBA, right? So there's A, and then there's epsilon, and then this is B. So this is AB is the first word, and then you have BB and A as the second word, right? So now you could also have, say, an arrow or a transition back from Q3 to Q2 over here, in which case you would have, you could have more words which get accepted by this transducer, right? But of course, I mean, this is just an example to show something simple. So now let us see how we can use these transducer to define succinct versions of Petrinets. So these are called transducer defined Petrinets. So such a TDPN.
So just a brief question. So why in the previous slide, why do you call your transducer to be asynchronous? Is it because of the epsilon?
Yeah. So it's because of the epsilon. So yeah. So yes. Because in a sense, if you think of it as there are two tapes on which you are moving two heads, then these two heads are not moving in synchrony, right? So you can think of it as the two tapes are two heads can move independently.
Okay.
Yeah. So actually, I mean, in our paper, so let me not get into that. So this in general, yes. So you can have such asynchrony which is there. But so here we have this succinct version of a Petrinet which has places which are defined by words of length n, right? So n is some particular fixed number. So for instance, suppose you have places p equal to p1, p2, p3, p4, right? Then this is sort of an explicit list of the places where in each of these places you can represent by a word, right? So say P1 is represented by the word AA, P2 is represented by the word AB, and then BA, and then BB, right? So here n equal to 2. So note that when we represent these places by words, so essentially for 4 places, we could represent it by words of just length 2, right? So essentially log of 4, right? So this gives us a kind of exponential compression, right? So what happens? So suppose you have a transition of this kind, right? So in our example, we saw this P1, and then you can take a token from P1 and put one in P2 and one in P3, right? So this is a Petrinet transition. So now this can be sort of defined using a transducer by having these states. So for example, look at this first transition AB. Essentially, this reads the first A of P1, the first A of P2, and the first B of P3. And then the next transition, which is ABA, reads the first A of the second A of P1, then the second, this B of P2, and then the A of P3, right? So so the language of this transducer is just this one tuple, right? AA, comma AB, comma BA, right? But now you could also have some other such transition, right? So you could have some other P4, P5, and P6 which have a similar kind of configuration where you take a token from P4 and then you put one in P5 and put one in P6, which will be represented by different words. But again, they will be included inside this single transducer, which tells you when is it that you can take a token from one place and put it into other places, right? So essentially, what you want to do is have, for transitions of this kind, there is a single transducer, which we will call T-fork, which will recognize all of these different possibilities, right? So you can take a token from a place on W1 and put one in W2 and W3, if and only if W1, W2, W3 belongs to the language of this transducer T-fork, right? Similarly, you can have transitions which are of the join kind, where two places go in and one place comes out. So such transitions have a different transducer T-join to identify when you can do this. And lastly, you can just have one in and one out, where you just have a transducer which recognizes not triples, but rather just pairs of words, right? So, so in this way, essentially, you can, given that if the Petrinet, if there is a Petrinet which has some kind of internal structure, then there is it's possible to sort of compress all of the different transitions of the Petrinet by using, let us say, small transducers, right, which recognize when you can make certain transitions. So, so now we can give sort of an exponentially larger Petrinet by specifying just 3 small transducers. So, and then we show that such succinctly defined Petrinet have a coverability problem, which is 2x space hard, right? So, and this is proved by adapting the Lipton proof. And it happens because, as I said, the structure of the nets that you get in the Lipton proof is amenable to a certain kind of compression. So, so I didn't get into the details of how this compression is performed, but I hope that what we are doing is sort of clear. So before I move on to reduce this, this succinct Petrinet coverability to safety, maybe I will just stop for a minute or two if there are questions.
So, so the reachability for Petrinets is now known to be Ackermann complete, right? So,
yes.
So does that mean this transducer defined version is strictly weaker? Is that?
No. So this is coverability. This is not reachability.
So what's the difference? Here's some notion of states. So.
No. So the notion of so the point is that so the TDPN, so this particular machine is something which is given to you as 3 different transducers, right? So this T-fork, T-join, and T-move, and some number n, right? So the number n is basically the length of the different, basically the length of the words that are used to represent the different places in the Petrinet, right?
Mm-hmm.
So now each of these words, W1, W2, and W3, these are all words of length n. So there are exponentially many different such words, right? So W1 is some word of length n, W2 is a word of length n, W3 is a word of length n. So each of these places is sort of identified with some word, right? And then you say that essentially this when you give these 3 different transducers, right? So this is sort of giving a implicit or compressed representation of a Petrinet, whose expanded form essentially will have exponentially many different places, one for each word of length n, right? Mm-hmm. And when can you move a token from some word W1, remove a token, and then put a token in W2 and W3, right? So this transition in that explicit and expanded Petrinet will be given by given by the fact that this W1, W2, W3 will be accepted by this particular transducer.
Okay.
So there is an implicit definition of the Petrinet, which is just comprising of these 3 different transducers, which are small, right? But then the explicit Petrinet, when you write it out in this format, right? When you actually write out all these transitions, this will be exponentially bigger. And now the coverability problem essentially is asking the corresponding coverability problem on this explicit exponentially larger Petrinet.
So my question is actually much more simple. So I just don't know. So what's the difference between coverability and reachability? So where is the difference?
So coverability means that you can reach a configuration where for every place you have at least the number of tokens that you have specified. Reachability means you have to get to a configuration which has exactly the number of tokens which are specified.
Okay. Thanks.
Yeah. So so let us move on to the reduction to safety. So now we want to simulate such a compressed Petrinet using our programs. So the idea is, suppose there is some place W1, which is represented by some word ABAA, and there is a token over here. So such a token will be represented by a thread which has a stack which has exactly this ABAA. Right? So this means that now if you have a marking, which means that there are no certain number of tokens in different places, so this will correspond to a program configuration. Right? So now the question?
Yeah, sorry. What does so here, for example, if you have a marking, so the marking will essentially say that in a particular, like in the different places, how many tokens are there, right? So this is
right.
what you call the marking. So yeah, I think this thing, when you say that this corresponds to the program configuration, could you elaborate on this a bit? Like
so in a sense, if you just ignore the global state for a bit. So then the number of different threads that you have, right? So suppose there are 2 tokens in ABAA, then there will be 2 stacks with this ABAA as the stack contents. If there are 4 tokens in BABB, then there will be 4 stacks, each of which have this BABB as their stack content. So if you look at the collection of all the stacks that is there in the program, then that will correspond to precisely the marking.
Okay.
Yeah.
So essentially each token in a particular place, it denotes a thread. And
yeah, exactly.
The place kind of talks about what is the sort of maybe the configuration in which that particular thread is in. Like if there are, say, 3, if a place has, let's say, 3 tokens, then all the 3 corresponding threads are in a similar configuration.
Yes, that's correct. That's correct.
Okay.
Yeah. So now the question is, how can we transit from one marking to the next? So suppose you have a transition in the net, which is like this, right? So there is some ABAA, and then from there you can move a token to BABA. So this means that you have in the configuration, there is a thread of this form, which you call the input thread. And now you want to remove this from the configuration, and instead to the configuration, you want to add this output thread BABA, right? So now there are a couple of challenges here. So the first of the challenges is, how can an input thread communicate its stack content, right? So we know that the total possible number of stack contents is exponential, right? Whereas the set of global states is much smaller, right? In a sense, it's polynomial. So you cannot just take the thread and write its contents into the global state and then make another thread for it, right? So this is a challenge. So the solution is we use
Ramanathan, sorry, I think so. This is maybe I did not fully understand. So when you say stack content, so I mean the stack can be arbitrary, right? I mean it's like a push down sort of thing, and the push down stack can be of arbitrary size, or maybe I
yes. But here, I mean, we are trying to simulate the Petrinet, right? So in this sense, we are creating a system which will have only a fixed height. This n, the number n that corresponds to the words which are there in the TDPN. All of the stacks will only have this height.
Okay.
Yeah.
But I mean, so you started with this context bound thing. So are you still in that in that framework?
Yes, we will come there. We will see where that becomes important. Yeah.
Okay.
So here, so this is the first challenge, that the stack contents are exponential, but you cannot just communicate it via the global state because the global state is too small. So the solution or the idea is to use what we call bit thread. So essentially, you pop the input thread while spawning new threads. So what does this mean? So we had this AB. So what you will do is you pop this A, and then you create a new thread which is just which just has A comma 1, right? So this is called a bit thread. So here this A comma 1 is a single stack symbol, right? So this is basically a thread with just like a single stack symbol which has this A comma 1, right? And now you pop the B, and then again while popping you spawn a new thread which just says B comma 2, right? So essentially you're remembering the bit numbers, right? And by popping all of them, finally you get something like this, right? So now the next challenge is how can we create the output thread? Because we have popped all of these contents of the thread, but there is no way to recombine these bit threads with few context switches, right? So here is where the context switch comes into play, right? So suppose if you have a stack of size 1, then you have to take one of these bit threads, see what it is, remove it, and then add it on top of this, right? Now then you have to get away from this thread, go to some other bit thread, read that, remove it, and then come back to this and put it on top, right? So this means that as you're building the stack, you will have to do many context switches, right? So, and we don't want to do that. Therefore, we guess and verify. So what does this mean? We guess the output thread content while spawning even more new threads, right? So suppose we have blown up the input thread to form this sequence of bit threads. And now what we do is we guess that the output thread has A as the bottom stack symbol, right? So we guess the stack content, and while guessing it, we simultaneously spawn this new bit thread. So here we have written that, A comma 4. But of course, note that this A comma 4 is in a different color because it's a different stack symbol from the green A comma 4, right? Because now we will have two sets of bit threads. So one corresponding to the input thread and one corresponding to the output thread. So now we can create this, we can guess this entire this thing, right? So we have guessed the contents of this entire thread while simultaneously producing these new bit threads, right? And now we can verify our guess by going through these bit threads, right? We can just go through these bit threads one by one, right? It's like we match up this B1 and A1, and then this A2 and B2, B3 and A3, A4 and A4. And so this transition is actually something that is done by this transducer, which is small, right? So there is some rule of the transducer, there is some run of the transducer which will happen, which will read these two words. And this can be done using the global state, right? So having done this, we can just, we have just gotten rid of all of these. So now the only thing that remains is this output thread, right? So we have managed to take this input thread and convert it into this output thread. So some details, what happened to the context switching? Remember that we create every thread without interruption, right? So because we are guessing, so we are spawning these sort of bit threads while we are guessing and building up the stack. So we never move away when we guess the output thread, right? And so we create a thread in one go, and then we only switch to that thread when we want to read it, and then it is destroyed, right? So this means that we only have one context switch. So we create the thread, and then when we come back to the thread, we just destroy it. Also, we only saw the move transition, right? But there were also these two other kinds of transitions, which are fork and join. But they are not very difficult because fork only guesses that only requires that you have to guess two input threads instead of one, and join requires that you have to read two input threads as well. So we have seen the proof of that concludes the proof of the lower bound. And in future, we would also want to consider restrictions other than context bounding. We can also think about sort of other kinds of scheduling than just non-deterministic. And we can also think about more powerful sequential programs such as higher order functional programs. In general, I think sort of the language theory for multi-threaded programs is not as well developed as, say, just for a single thread, right? Say for a PDA. So this is something that we would like to investigate more. And such, I think this is still very much relatable and relevant to what is going on right now. Yeah, so thank you. And if you have more questions, I can take them.
Thanks, Ramanathan, for the talk. So yeah, so we have time for questions.
So there is a question in the chat which says context bounding seems to be a semantic restriction. Is there any work that verifies that a given arbitrary multi-threaded program is a context-bounded program? So, so I mean, if you have, you could actually store the context bound in the stack, right?
Kushal, you may speak up, like if you may unmute yourself and.
But that's only dynamic verification. That can you do that statically? That storing in a stack.
Yeah, no. I mean, you cannot. How can you know, right? Because it's something affiliated with whatever thread you are running. So, so you mean you want to like have you want to, given some program, you want to know, is there some k such that you know, all the runs will be bounded by k?
Yeah, I think that's what probably. I don't know. Maybe you can.
I see, but I mean, I think you would. I think it would be difficult to do such things, right? Because then the original program you are starting off with is actually Turing powerful, and then you are asking a non-trivial property about the program.
The program, not of the language. Yeah.
Not all programs be context bounded. Sorry, what do you mean? Not all programs would be context bounded?
I think Kushal is having some problems with the mic. I'm not sure what the right solution here is.
So I think, yeah, so his question is that, is there any work that verifies a given arbitrary multi-threaded program is a context-bounded program? So I guess, Ramanathan, you already answered to this, right? Like saying that this is like an arbitrary program, and then which is like an arbitrary Turing machine, and then you are talking about a specific property of that which should be undecidable.
Yeah, that's what I think, right? Because yeah.
Mm-hmm. Yeah, so I was also thinking that, so here, for example, this k is specified in the beginning, right? Like, so does it make sense to ask this kind of question, that does there exist a k for which you want to verify the safety property, or I mean, I mean, what if like the k is not specified in the as an input? Some kind of, if I talk about some kind of finite number of context switches are possible. So all I know is that there will be finitely many context switches, and then I talk about some verifying safety properties.
No, but so finite doesn't make sense, right? I mean, it will I mean, any particular like run up to some point, you would have performed some number of context switches, right? So I don't see how finite So, but I mean, what is the kind of property you would be? So firstly, are you talking about safety? So
yeah,
you want
I'm talking about safety, which is similar to
okay.
the reachability properties that you were talking about.
Okay.
But suppose I do not know the K a priori. So if, for example, I don't know how many context switches are going to be there in the in my threads, right? So then does it make sense to talk about, like, if I know, but there will be some finite number of context switches at most in the threads.
So are you asking like for a weakening of what Kushraj said, which is I mean, basically, does there exist some K for which already all the behavior is there inside this K? Is it that kind of a question?
I mean, yeah. So in fact, I thought of this from Kushraj's question only,
yeah,
but like,
exactly.
so
That's what I was asking, whether there exists a finite number K such that all the runs or all the runs are K context bounded.
So I think this is what Kushraj's question
Yeah,
is.
that's what I was asking. Am I audible now?
Yeah. It's the volume was a little low, but yeah, you're audible. No, I think this should also be undecidable, right? I mean, I don't see because.
So there is this work on these counter machines and vector addition systems where they have this where they verify that a given system is K reversal bounded or not. Right? In general, either it's non-elementary or it's undecidable. So in some cases it becomes decidable. So in some sense, reversal boundedness is very similar to this.
But no, but you are not talking about the initial model that you have has partially blind counters, right? So there is no zero testing. So the initial model that you're talking about is not Turing powerful.
No. In counter machines there is, right?
So you do have a zero test.
Yeah. In Minsky machines also they have this reversal bounded verification. But in general, of course, it's either non-elementary or undecidable. Even if I remove zero test, it becomes non-elementary, right?
Right. So, but with the zero testing, and if you start with a model which is Turing powerful, then I mean, it could be undecidable, right? So
these are not same restrictions. It could be undecidable. That's what I'm asking. But there is no yes or no answer, right, in the literature, as far as you know.
So I haven't seen this, but yeah, I can take a look. But like I said, my gut instinct would be that like, yeah, you would not be able to decide any of these things.
I see.
Yeah.
Completely. Is it clear that just 1 second? So there is a question in the chat. Is it clear that the property given K, the input for
Yeah, this might be a completely like miscarried things. That's why I just put it in the chat.
I see. Okay. So I see. I see. So your point being that I think this was also maybe the point that Kushraj was making, which was that this is not necessarily a property of the language of the RE language, but rather of the machine.
Yeah.
And so if you ask, I think your point is that if you ask, there are certain questions like this that you can ask, such as does it halt in K steps, which would be decidable because you just have to run it for K steps.
Yeah. It's clear that doesn't work for this case, but
right. So yes, so also here, I mean, there is non-determinism, and you want to know whether all possible runs of the program are So clearly, the one thing is that it's clearly possible to just create two threads which pass control back and forth between each other, right? And you could also set up this device to activate when you reach a particular global state, right? And yeah, I'm just trying to see if there is some easy proof to show that this is undecidable, but I will think about it.
So I was also at the, I mean, so you were talking about also other kind of boundings, right? So, so do you know if these any of these proofs will work for some of the, I mean, there are these face bounded or scope bounded. There are other kind of boundings which also talk about like by restricting you get some decidability. So
yeah, so I think one of, I don't remember which one this was. So I think one of the other notions has this notion of whenever you push a particular when you push a particular symbol onto a stack, then you can switch away to some other stack so many times before you pop this symbol, right?
Yeah, I think this is called the either the scope bounded, possibly is.
Maybe this is a scope bounded, but so here the thing is that like so here already, so whatever number of switches that you have made, so there is some first symbol that you have. So this number already dominates the number for all of the symbols on top of this, right? Because they were pushed after this particular symbol, right?
Okay.
So here, because we have this notion of spawning, right? So whenever you reach the bottom of the stack, you can just sort of spawn a new thread.
Yeah.
So essentially, I think this scope bound, I think this particular restriction just reduces to the context bounding case for in this model.
I see. Okay. So you were essentially saying that even this. Okay, but this is not about the hardness. So this may not give you. So you were talking about that taking the scope bounded, it can be reduced to context bounding, right? It's not the other way around. So the hardness may not still go through, but maybe the membership might be possible.
Yeah. Okay.
Basis. Like you were saying that it might still be like 2xp.
We haven't explored like sort of all of the complexity for some of these other restrictions. I think there was also something more recent which was called whole bounded or something. So there are a number of different restrictions which we could also look at. Yeah.
And other than safety kind of sorry.
No, so I was just going to say, I mean, there is also the question of, from some practical standpoint, like, which of these would make more sense and things like that. So that's also there, but yeah.
Yeah, and maybe one more, just last question. I was also, so apart from safety, what are the other interesting properties for this multi-threaded kind of programs are interesting? I mean, one is determination, but
so generally, I mean, in a sense, safety and liveness are the two quintessential things, right? So I mean, and then you can sort of see every other property as a combination of these, right? And so that's why. And I mean, the other thing is, for instance, if you have some property that you can say write in LTL or something, then you could convert this into an automaton and take the product in the global state space and do the thing, right? So this sort of also increases the scope of what kind of things you can check.
So essentially, what you were saying, that if you can solve the safety and the liveness problem, then the LTL, like if you have properties which are specified in LTL, solving that should be kind of straightforward.
Yeah.
Okay. So liveness properties can include like termination, these kind of things, right? And important.
Yeah. So termination and this fair, essentially the fairness part is what was particularly difficult, right? So because so I think termination in a sense is easier, but fair termination is much more difficult because you have to sort of keep track of certain numbers and you have to know. Yeah. So essentially you cannot. So in this talk, I mean, we didn't talk about the upper bound much, right? Because I think I just wanted to focus on one of the results and give some of the details, right? So I didn't get into generally what are the techniques that are used and what kind of things are there and what is where do things break and where do we need newer techniques or like what kind of things do we need to do. So so one of the things for the upper bound typically is that are you one minute? Are you also looking at relaxing the idea of global state to more relaxed models like RA and talk about these results? Sorry, can you tell what is RA?
Okay, so you have been talking about global state where I mean all the thread probably agree on the value of global variable, right? But most of the modern processors nowadays don't have this guarantee, which we know as sequential consistency, which results from this scheduling instruction from different thread and having unique, let's say, function, I mean, which determines value of each global variable. And every, let's say, processor knows that function. So yeah, so they're known as, I mean, relaxed model, like weak memory models, where yeah. So you don't, I mean, it is, I mean, quite natural in those models that different processor may have different may see, let's say, different values for these global variable at the same time. I mean.
Yeah, so I think this would definitely be interesting. We have not done it. Yeah, so for instance, I understand that there are even weaker kind of models, where people study these like parameterized systems where you don't have these atomic read writes. I think every thread is just allowed to write into a space or it can read into a space. But in a sense, there is no locking mechanism such that something is accessing a memory spot and then it locks it and then it can read and then write in one motion, right? So I think those kind of systems typically, I think that is much more relaxed in the sense that severely weakens the amount of communication that can happen between the threads. But maybe what you are suggesting is probably something in between, right? So it's not. In a sense, it's not as relaxed as saying that there is no way to, you can just read or write at a time. And the one that we have where like essentially, in a sense, there is a way to lock something so that only one thread can be accessing it at a time.
Okay, so this RA model actually has one atomic command also that you were mentioning, RMW they call. So you have an atomic read and write, but even with that, for finite number of threads, some this reachability problem is known to be undecidable actually. So
I see. Oh, so this is, I find this very interesting. So I would appreciate it if you could, sure. If you would like to talk more about, these things.
Yeah, sure. We can continue.
Okay, so if there are no more questions, then let's maybe end the talk here and then in the session here, and let's thank Ramanathan again for the very nice and interesting talk. So thank you, Ramanathan.
Thank you for having me here.
Yeah, thanks. Thank you.
Okay, so I'll close the meeting now, Rajesh.
Yeah, please.